Hi guys, my name is Rahul Best and in this video I'm going to present IEEE paper about brushless double-fed induction machine as a variable frequency transformer. This paper is written by Abdel, Khalik, Elserougi, S. Ahmed and A. Massoud. A variable frequency transformer has been recently used as an alternative to HVDC to control power flow between asynchronous networks. VFT consumes less reactive power than a back-to-back HVDC system. A VFT provides faster initial transient recovery and has a better natural damping capability. A VFT is simply a doubly-fed induction machine where the machine torque controls the power flow from stator to rotor. The main disadvantage of a VFT is the slip rings and the brushes required for the rotor circuit, especially in the bulk power transmission. The brushless doubly-fed machine Bdfm with the nested cage rotor machine is proved to be a comparable alternative to conventional DFIM in many applications, with the advantage that all the windings being in the stator frame with the fixed output terminals. Interconnection between power networks can be classified into synchronous and asynchronous ties. Synchronous ties are the most common type in practical power system. However, synchronization between involved networks is necessary to ensure effective power transfer between them, which is a challenging task, especially with weak networks. On the other hand, asynchronous ties can be used to directly connect two power networks experiencing a slight difference between their frequencies. HVDC transmission is widely employed as being advantageous for long distance bulk power delivery and asynchronous interconnection. Recently, variable frequency transformers are recognized as a promising candidate for bidirectional asynchronous power transfer, offering many advantages over HVDC transmission. The VFT technology was first introduced in the early 2000s. The world's first VFT for bulk system power transfer between large asynchronous power networks has been successfully installed and tested at Hydro-Québec Language substation in Canada. VFT provides isolation between networks, it improves grid stability, meets power transfer needs during normal condition and supports during fault condition. So, till now we can come to a conclusion that why we are using a VFT rather than a HVDC transmission. Well, that's because we have a few merits, and the merits are less reactive power, less harmonics, faster initial transient recovery, and better natural damping capability. Now the question is how we can control power flow using a VFT. A VFT is simply a doubly fed rotating machine which is connected to the involved asynchronous network to achieve its function as asynchronous tie between the two networks. The rotor speed is controlled to operate at the slip frequency between the two networks. When two networks with the same frequency are connected, the torque on the shaft is controlled at zero speed. The angle of the rotor is positioned to achieve a scheduled power flow by the means of a DC drives. Being an effective mean to control power flow in weak interconnections, the VFT is also used to reduce power fluctuations of large-scale grid connected to offshore wind farms. Doubly fed machine with nested cage rotor machine provides advantages that may warrant its application despite an apparent power density penalty. It was proposed as an alternative to conventional DFIM in many applications, especially in variable frequency, variable speed drive for large induction machines, wind applications, and contactless power delivery systems. The main advantage of brushless variable frequency transformer is that all machines winding is in the stator with the fixed output terminals. Here, we will use a Bdfm with nested cage rotor to functionally replace the conventional VFT to interconnect two asynchronous networks. A BVFT is presented to overcome the brushes problem. The theory of operation of the proposed system is first described. A prototype machine is then designed and its inductance are calculated using the modified winding function. Based on the suitable transformation, the DQ model of this machine is then presented and used to simulate the machine in different operational model. BFT is simply a BDFM with nested cage rotor. The stator comprises two three-phase windings with P1 and P2 pole pairs. The rotor is a nested cage rotor with number of nests equal to the sum of stator pole pairs. The nested cage rotor has the same construction as a conventional squirrel cage rotor. The main difference between them is that in conventional squirrel cage rotor, all the bars are connected from both sides with the two end rings. However, in the nested cage rotor, the bars are divided into P1 and P2 groups. The selection of the suitable number of poles is a design factor and depends on many factors such as magnetic saturations and radial forces. In the proposed design, the selected number of poles is 6 by 2, stator winding pole numbers combination. The selection gives an approximate quasi-square flux pattern and shows great promise in many applications such as wind power generators and pump drives. Of the proposed system is shown in this figure, and the machine construction is like this. The capacitor banks that you can see in the figure number 1 are designed to supply the reactive power required for the machine magnetization. Of the proposed BVFT is similar to the conventional VFT using DFIM, where the BVFT is used to connect two networks experiencing a slight difference between their frequencies. The two networks are connected to the two stator windings. The power can be transferred from one side to the other side by controlling the torque applied to the machine. Generally, DC motor is mechanically coupled on the BDFM shaft. For control the shaft torque and hence the amount of transfer power between the two involves asynchronous networks. The power transfer magnitude and the direction will completely depend on the torque applied by the DC drive. For example, if the torque is positive, the power will be transferred from first stator winding to the second stator winding and from second to the first. The rotor of the VFT spins at this speed that is proportional to the difference between the two network frequencies F1 and F2, and that is given by the equation. The stator frame of an existing 3 horsepower squirrel cage induction machine is used to build a prototype PVFT. The stator is rewound to accommodate two stator windings with 6 by 2 pole combination. The number of turns per phase for both the windings and their cross-sectional areas are selected to ensure the same acceptable air gap flux and power. A nested cage rotor is designed to fit into the machine stator. Machine design. The prototype machine will be constructed using an existing 380 volt 3 horsepower squirrel cage rotor induction machine. The design is restricted with the stator dimension given in this table. The stator is rewound to house two stator windings with the dissimilar pole numbers P1 and P2. The suggested number of poles are 6 and 2. A nested cage will be built with the same diameter as the old rotor. All the dimensions of this induction machine is given in this table. Now let's move to the stator design. The stator is wound with two single layer windings. The two layer comprises the 6 pole winding while the upper layer houses 2 pole windings. Since an existing stator is used, the only design criteria is the number of turns for each winding. The stator coils are fully pitched because each winding is wound with only one layer. For total number of slots, 36, the number of slots per phase per pole for the 6 pole and the 2 pole windings are 2 and 6. Since it is required to replace the single 3-phase winding of the existing induction machine by 2 separate 3-phase winding, hence the rated voltage for the both stator winding is selected to be half that of the existing machine of 110 volts. The current rating for both the windings will be selected as same as that of the induction machine. Fill the following requirements. First, the magnitude of the MMF produced by the 6-pole winding is half of the 2-pole winding to ensure that the peak value of the total MMF equals the 2-pole winding when fed separately with the rated current, and this is as shown in this figure. Now the back and flux with the both winding carrying full load current will not cause core saturation. The design. A nested cage rotor. the number of rotor nests is chosen equal to the sum of pole pairs of the two stator windings P1 and P2. Hence, for the selected number of pole pairs, the required number of nests will be 4. The number of loops per nest n is chosen to minimize the MF harmonic content. As the number of loops per nest increases, the harmonic content decreases. Typically 3 to 6 loops per nest are used. The selected number of bars is 40, where each nest has 5 loops, as shown in this figure. Same bar dimensions as the existing rotor will be assumed for the design of the rotor and is used to calculate the resistance of different nested loops. After the rotor design, we have to move to the machine modeling. The machine is modeled using the conventional DQ model. The machine modeling commences with the inductance calculation using the modified winding function, and based on the machine dimensions, then the corresponding DQ model is present. Now we have to do the inductance calculation. The first step for the machine modeling is to calculate the machine inductance matrix. The modified winding function method is used to calculate the machine inductance matrix. The general expression for the mutual inductance between any two circuit I and J of any electrical machine is given by this equation. Prototype machine, there are 6 turn functions for the stator windings and 20 turn functions for the rotor nested loops. First, all the functions are calculated as a function of the peripheral angle. Then, substituting in the given equation, the inductance matrix element as a function of rotor positions are calculated. The inductance matrix dimension will be 26 by 26. In this case, to simplify the machine model, to reduce the number of equations and to eliminate the inductance dependency on the rotor position, a DQ model is obtained from the phase model through suitable transformations. The final dimension of the resulting inductance matrix will be 14 by 14, but with constant coefficient. Each stator winding is represented by 2 DQ coils. Each group of loops having the same color as in this figure of the nested cage rotor is represented by 2 DQ coils. Hence, the rotor will be represented by n coils in the t-axis and n coils in the q-axis. For the prototype machine, the total number of the coils will be 14. The DQ model of the Bdfm is represented by these equations. The flux linkage vector is given by these equations, and the torque equation is given by these equations. To perform these simulations, let's talk about the simulation result. The system is simulated with the same controller of the conventional VFD. This controller ensures the following requirements. First, the rotor speed is regulated at synchronous speed that depends on the difference between the two network frequencies. And the second, the shaft torque is controlled by the means of a DC machine to achieve a scheduled power flow between the two networks. The proposed system is simulated with the 110 volt 50 Hz networks, denoted as network A, is connected to the 6-pole winding, while the 2-pole is connected to another 110 volt network, denoted as network B, that experiencing frequency variation. The frequency of the second network is assumed 49 Hz. Hence, corresponding synchronous speed for the two frequencies will be 15 rpm. Firstly, the two networks are synchronized. The DC machine is controlled with reference torque shown in this figure. The two stator winding powers are shown in this figure. The machine speed is shown in this figure. Now, where the speed remains synchronized at 15 rpm respective to load change, it's clear that the power transfer between the two networks follows the torque reference. The positive torque applied to the shaft, power is transferred from network A to network B. The relatively large difference between the two stator winding powers is due to the relatively high machine losses corresponding to such low power ratings. The system with the high power rating, this difference should be negligible. The RMS current for the both stator windings are shown in this figure, while for the nested loops are shown in this figure. It is evident that the outer loops of the nested carry much higher current than the inner loops, which can cause an unequal current distribution. This unequal current distribution between different rotor bars yields unequal rotor heat distribution. Equal current distribution can be tackled by using rotor bars with different cross-sectional area, larger cross-sectional area for the outer loops and lower cross-sectional areas for the inner loops. An important reason that justifies why multiple rotor loop model is used in this paper rather than the much simple single loop representation. The non-negligible phase shift angle between the currents in the different loops in the same nest, as shown in this figure. Now, the angle changes as the machine is loaded. This gives a significant error if the whole nest is represented by a single coil. The proposed BVFT is shown to be an attractive alternative to conventional VFT, while retaining the advantages of the absence of the brushes and the presence of all the windings in the characteristic curve in per unit representing the machine winding powers, currents, and efficiency are shown in this figure. The base values are defined as the values corresponding to rated winding current. The efficiency is defined as the ratio between the transmitted power and the received power between the two networks. It is notable that the output rated transmitted power at the rated current is approximately 60% of the existing 3 horsepower skill gauge machine. This is due to the non-optimal design of the machine since an existing machine we are using to build the prototype one. However, the machine optimal design is expected to increase the machine power density. This machine type is generally disadvantageous due to the relatively low power density when compared to the squirrel cage machine. When it is compared with TFIM with same power, the power density penalty will be less. This may warrant its application with the fixed output terminal advantage obtained. Come to the conclusion. In this paper, we proposed a brushless variable frequency transformer that is based on the conventional brushless W-fed machine to control power flow in weak interconnections. Its two stator windings are used to connect two networks experiencing a slight difference between their frequencies. By controlling the shaft torque using a DC machine, the power flow between the two networks can be controlled in a much similar way that in a conventional VFT. The winding function method is then used to calculate the machine inductance. Then we used the machine inductance equation to develop the machine DQ model. Now, despite an apparent power density penalty, the simulation results show us that the proposed BVFT may be an attractive alternative to a conventional VFT while retaining the advantages of the absence of the brushes and the presence of all the windings in the stator with the fixed output terminals, which is much suitable for the bulk power transmission. Thank you.